Last time we derived this series expansion for the natural logarithm of a number. The derivation involved use of the geometric series. In this lesson, we will use it to compute an actual number. On this slide, I have also included the sigma notation of this infinite series. Notice that I have substituted z equals 1 plus x over 1 minus x. It can be helpful to think of the argument z as a single number for which you want to know the natural logarithm. But we need to evaluate the series in terms of x. Here is some simple algebra to solve for x given a value z. Pause the video if you need to follow through the details. The important part is the result in the last line. Suppose we want to know the natural logarithm of 2. First, we must compute x equals 2 minus 1 over 2 plus 1. This equals 1/3. Underlined in green is the decimal representation of that. Here is a spreadsheet representing the series expansion seen on the first slide of this lesson. Notice we start with 1/3, underlined in green. The rightmost column is 2 times the sum of the terms in the third column. Notice by the last row we have 10 digits past the decimal. This can be seen by the 10 zeros underlined in purple. Also notice the digits underlined in red. Within rounding, they all match the corresponding digit in the row immediately above them. What if 10 digits isn't enough? Can we do better? Let's try the square root of 2. This can be found fairly easily with Newton's method or some other root-finding algorithm. Plug it into the expression to find x, which is approximately 0.17, as underlined in green. Now plug that value of x into the series expansion. A spreadsheet of those calculations is shown here. This time we got 15 digits of accuracy past the decimal. This is seen by the 15 zeros underlined in purple in the third column. In the fourth column, all the digits underlined in red exactly match the digits above them. These can be helpful guides when trying to estimate how well your answer has converged. So why did we take the square root of 2? It turns out we can use the law of logarithms boxed in green to assist us. We just found the number underlined in red. The square root of 2 squared equals 2, so we can simply double the natural logarithm of the square root of 2. This gives us the final answer underlined in blue. Compare that to the answer from a built-in function. Notice that every digit except the last one matches. I'd say we didn't do too bad. Of course, if we wanted to do better, we might try to make x even smaller before plugging it into our series. How do you think we could make x smaller? To use the built-in function on a scientific calculator, you must press the button boxed in blue. The natural logarithm of 2 is found by pressing 2, then ln. This particular handheld calculator only displays 9 digits total. I used Excel to make the spreadsheet, and that displays 15 digits. Excel and other computer software have their own built-in functions for finding logarithms. I'd encourage you to play around with these to gain some familiarity. This same series expansion can be used to find the natural logarithm of other numbers. My example was for z equals 2. Try it for a different number. Tell us what you get in the comment section below. The best way of learning mathematics is by doing it, so practice as much as you can until you master this material. In the upcoming lessons, we will be exploring more properties of logarithms, how they relate to exponential functions, and how we can use them in computation. I appreciate your support and look forward to seeing you again.